Okay, everybody take a deep breath. Particularly me. This is Roger's talk. Roger, for those of you who've not been here before and not watched any of the YouTube videos, we very often have Roger give the last, or I think always have Roger give the last presentation at the UGM. He normally makes me want to cry. Not really. He says bad things about the RD kit in a constructive way. So I think what's important for you to take away is that though you may not see it, whatever happens here actually does end up being constructive. We get a lot of pull requests out of this. And Roger is very good about directing this kind of stuff at me and at Brian, and doesn't normally direct it elsewhere. So Roger, take it away. I'm waiting with bated breath. Do I need flame-proof clothes
No,
this time?
I'm hoping that it's hope to say lots of nice things about RD. I get that on there. Again, thank you for Greg. The way I often think of this is that most of the user group meeting is for the users. It turns out that Greg and I have a strange communication channel. He blogs every week, and I once a year have to stand back and try and defend the other side of the argument as it goes on. But to provide a teeny bit of context, it's getting very old now. Since I've been coming to these, was it 14th RD kit UGM? Is that many years ago, I wrote a molecular graphics program called Rasmol, displaying molecules on the screen. And at the time, it was one of the most popular programs of its kind with over 1 million users around the world. But of course, it was my first exposure coming from the world of structural biology, actually, computer scientist by background, to the fundamental challenges and the interesting, tectonic shifts in cheminformatics. The two main file formats were PDB files and MDL mol files. And I was always confused that no matter how you tried to convert them, you lost information going both ways. If you have a mol file, you have bond orders and isotopes, and you turn it to PDB, and all of that gets lost. If you had a PDB file and you turn it to a small string or a mol file, all of the residue information got lost. And so essentially, Greg and I have spent, our careers, trying to tackle this fundamental or interesting problem or challenge in what's gone on. What's interesting, and Greg sometimes teases me about this, is the way that certain types of problem come in and out of vogue at regular intervals. And so it's interesting that, for many years I was on Helm technical advisory committees, and it was never going anywhere. Mysteriously, the entire field has now had an interest in doing biopolymers are the problem of the year. The first thing I should start out with is truly how wonderful or revolutionary one of the points that Greg covered in his recent additions to RDKit. The support for atropisomers in smiles. Tadhurst's extension in RDKit of a chemaxon underlying extension. Some people consider it a hack of a hack, but it truly solves, a very major and very fundamental problem in how these things are done. Jan, who's in the audience, has spent a lot of time trying to extract, smile strings from CST structures. And nowadays, we should be able to try and capture for real 3D structures or crystallographically determined structures what the atropisomers are and which ones are locked. As Greg and Brian point out, the output of conformation generators don't really imply what the atropisomer was known. And so there is a subtle shortfall there. But it's interesting, I was at the ACS meeting in Washington, D.C., 3 weeks ago, and interesting, several of the first-time disclosures were atropisomer based in FDA approval. So clearly it's a technology of its time. So having said the wonderful things, we then start on the not so good, or this is where we start applying the pressure to Greg, is that having completely revolutionized and pushed the state of the art in stereochemistry by supporting atropisomers, there's this interesting issue of alenic stereochemistry. And the thing that will embarrass, Greg the most, apart from it's passed in the RD kit and then completely ignored. There's an enum that's defined, but then never used anywhere in the code. This was supported by Daylight in the 1980s and 1990s. And just as importantly is Inchy. If you use RD kit to generate an Inchy string, I mean, Greg doesn't yet pass through the Alenic stereochemistry in order to get the string out the far side. As he said, it should be tetrahedral center of extended center. Greg's looking at me knowing it's like, oh, this will be done by the end of the hackathon tomorrow, which is why we then mention and add these sort of things to the wish list of what could easily be done. It's pushing the state of the art. One of the other things that's phenomenally interesting or added recently or a few years ago was the huge improvement in inorganic stereochemistry, non-tetrahedral stereochemistry being added to the RD kit. At the time, there's a lot of work, there are a lot of progress that is made for octahedral stereocenters having 6 neighbors and trigonal bipyramidal centers having 5 neighbors. But the thing is we've now reached the point we can go a step further. There are things with open valencies, essentially seesaw compounds. If you imagine an octahedral center where only 5 out of your 6 neighbors exist, so in the middle at the top, I mean, the Haveda-Grubbs compound is phenomenally important in a certain class of reaction and yield analysis, which enantiomer you get out. These class of compounds, I mean, essentially hypervalent sulfurs with fluorine, were again one of the topics of Greg's PhD thesis when he did this. So he knows perfectly well that these types of compounds exist, the ability to handle them. And you can see here is that the code is already in RDKit. The octahedral permutation 19 is just the extension, or now that the code has settled all the dust, the flame wars, fights have settled over full octahedral, is then handling the implicit hydrogen or the unfilled valence. In the same way as S-omeprazole and S-oxides, tetrahedral centers that only have 3 neighbors, you can do the same thing here. One of the other things that, again, I'm truly awestruck by, jealous is probably the not too strong a word, is the huge improvements made in RDKit, for example, for things like multi-centered bonds and hapticity. Greg skips over it very quickly. It was interesting, he's complaining that now he no longer has Marvin, he can't draw any of these structures anymore, and so the ability to read them from PDB files or from ligands. But these are the types of molecules where essentially you're bonding to a ring system, so the ferrocene type molecules, or what are called piano stool-like compounds. And so one of the things that the Greg and RD kit supports is this chemaxon extension of the multi-centered bond, Varatachin B3000, that allows us to now handle types of compounds or types of stereochemistry, which inorganic chemists find phenomenally interesting, but has been lost, the baby with the bathwater going previously. One of the reasons I bring this up is to essentially to serve as a warning for the Inchy folks, Gerds in the office and others, is that an interesting class of stereochemistry has come to light where people are saying it's like, oh, well, how are you going to start working with ferrocene stereochemistry, where you have 2 sandwiches stacked on top of each other, and there is an interesting axial chemistry through the iron, and how is one going to go about doing that? There's even papers and proposals for specifying new types of M and P-like annotations to this. The thing that I'd like to point out is that stereochemistry has nothing at all to do with ferrocene, or it isn't unique to ferrocenes. For any asymmetric ring system, you can imagine an ion a metal atom coordinating either above or below it. So even with a half sandwich, there is a stereochemistry. If you have tryptophan in the active site of a protein or a matrix metalloprotein, how the zinc is coordinated is defined by, am I above the plane of the ring? Am I below the plane of the ring? And of course, the multi-center bonds gives us a handle on how to tackle that. This is, of course, and then part of the upgoing backwards and forwards. Should it be supported? How would it be supported? What can be done? In 2023, I had a proposal, and I'm now retracting, and this is the wrong way of doing things. But it proposed that one of the ways of trying to capture this type of stereochemistry was recorded in the chemaxon unattended smiles, the permutation of the atom orders as you went around the ring from left to right. As Greg knows, this creates a huge complication for writing smiles, canonicalization, getting the atom orders right. It's not quite the right way to solve the problem. It actually turns out with the wonders of multi-centered bombs, the asterisk or the center point atom, the multi-center that you're dealing with is the point in the molecule that has the stereochemistry. And of course, then just adding, for example, am I at or at, am I clockwise or counterclockwise on the atom that forms the multi-center? for 10 minutes. 1, 2? Yeah. Brilliant. Thank you very much. Brilliant. Thank you. And then purely to blow, I mean, just Greg's mind in the audience on how you think about this and how you don't think about this. The same problem as you have with double bonds in MDL mol files and atropisomerism is, well, what happens if you had stereochemistry and the chemist didn't intend to draw it? Just because something's laid out in 2D or drawn in a certain way doesn't imply that the stereochemistry was known by the chemist at the time. And so again, the proposal here, I mean, makes sense in hindsight, but the use of a squiggly bond to the center of the ring saying, well, I don't know which way around or what orientation the far side of the ring is, but it builds upon, the existing atom types in CDX and CDXML files that Greg now reads very well and marveling for multi-centered bonds. Purely because I've mentioned easier, I mean, I'll skip over this, but there's some marvelous math in is a ring system handedness and how do the symmetry groups map into that? I think there's a talk today on NMR that showed that if the number of unique symmetry classes is useful for determining. Another example of, I mean, something it would be nice to support is that Greg, I mean, another phenomenal improvement in making us try and catch up with how fast Greg is moving, is a support for generic and homology groups. I mean, in Raxis, I mean, and similar search algorithms. Marvelous blog post on RDKit support for things like alkyl, heterocycle, I mean, carbocycle and aryl. Here you can see, for example, ChemDraw and the marvelous way of drawing or specifying this. One of the things I only started noticing as you then try and use it with the new RD kits is it writes out an interesting variation of smiles, open square brackets, ALK, close square brackets, or open CBC, close CBC. That clearly ChemDraw smarts or ChemDraw smiles is a strange way of doing things. But this is also then a good hackathon level project that it's relatively simple to spot that in the smart string and convert it to the Chemaxon, the preferred format that RDKit uses internally of specifying it with the atom names and types afterwards. And then I come to the controversial topic of the meeting, or the first of many, the myths of biopolymers. And I stand here not to say there's a better way of doing it, but essentially the number of cuts and scars that people have endured trying to handle the problems of biopolymers and sort of mistakes that the Helm folks have made, not the people in the audience, but Helm itself. Myth 1, that there are a small manageable number of monomers. And so SCSR, in bioinformatics, you have 4 bases or 20 amino acids. That should be easy to handle. That there's a one-to-one mapping between monomers and atom representations. And that Helm and the new monomer mole is sufficient going forward. It turns out that in real life, biology is far, far worse and far uglier than we think it is. It turns out an analysis of PubChem from earlier this month, 35,000 different amino acid monomers, over 20,000 beta amino acids, a huge number of different nucleotides, monosaccharides, different substitution groups, 1,404 fatty acids. Brian Kelly has often told me, why do I do this to myself as a personal Vietnam? But clearly things like lipids, which truly no one on the planet cares about, are so mind-numbingly complex that it's just a huge amount of effort to support them. And so to explain or put that in context is that solutions that try and use with monomer databases. It's interesting, the various people talk about Helm, all of their to-do lists were somehow in RDKit, we're going to have to specify how the amino acids and the monomers are put together. But of course, derivatives and various forms, substitution, deform, Helm, for example, for every amino acid, you have to specify the D amino acid. For every form, you have the alpha methyl variant, the D, the L, the D and L, if you're coming from a small string, is that the combinatorics multiply out, that Kemble, for example, end up just referring to as monomers as X1834 or X456 or X, that clearly almost unintelligible or unhandleable. The first thing I'll say is that handling the 20 standard amino acids, of course, is the biggest win. This is a log plot on the side that says, well, as a data compression technology, supporting or hard coding, the main amino acids, the D and Ls, and the most common things, gives you the greatest win by far. The very long tail means there are only some monomers that are only worth representing or seeing once. And exactly like SCSR, or ChemDraw CDX files, it makes sense to store the monomer definition in the string described as monomer. So examples of this, and going forward, I'll come back a teeny bit to this because it was a recurring issue or a niggle that I had. Of course, is the representation or how do you draw biologics. In chemistry, we would never think of using network X or cytoscape to draw the 2D depiction of a small molecule and expect to show it to a chemist. We spend, Dave Cosgrove and others have spent a huge amount of time producing fantastically nice layouts. Biologists have, very clear expectations of what it is they expect to see and how things should be presented in papers and FDA filings. So, for example, amino acid sequences running from left to right at several points today. I'm not sure if people noticed, there were peptides that went right to left on the screen, that the average biologist would make their eyes bleed. That is, it's not the way of thinking about this. Of course, it's neither Schrodinger nor collaborative drug discovery nor data grok's problem that this is this is an issue. It's the underlying Helm library and the functionality there. I think one of the great contributions that RDKit could make is a better form of visualization for those Helm styles and monomers that would then be taken up. It's one of those rots in the industry that percolates into other people's code. Here, for example, showing the marvelous all-atom representation and how it then shrinks down to interesting disulfide bridge and put together. Michaela talked today about interesting polymers and dendritic polymers. Jean-Louis Raymond, who most people know from the world of GDB, has an interesting habit of trying to make amino acids and peptides that link together in truly odd and awkward ways that have no start and no beginning. Many of the perception algorithms that people say, here I'll take a small string, can I read it from it, will need to handle some of the strange cross-linking and the non-standard representations they use. I'll skip over, sugars are even worse. But just as importantly, that they have their own community and very strict rules for how they're displayed and drawn on the screen. My ex-colleague Noel O'Boyle, who worked on the SVG output of this, would be involved in huge flame wars with the standards committees on the RGB values used for the red and the green and the blue. That clearly they are very specific on exactly what they want to see and how it's done together. So all atom representations that look incomprehensible, and then how one goes about displaying those. But one of the reasons why I'm not so keen on Helm or the simplicity or assuming the Helm-like approach is easy is that fast data smiles is the easy bit. That having a single one-letter sequence and turning it into an all-atom representation is just a matter of dictionary lookup. Far more interesting is going the other way. Given a smiles or a mol file, what monomers do I have? Histidine, for example, has several tautomers. Hid, he, hip. Essentially the protonated and unprotonated forms of amino acid side chains, the zwitterions, representations of azides. Someone even mentioned it's like, certain classes of amino acid monomers that had atropiosomerism in them that are now handleable by RDKit. But essentially anyone that tries to use a database or a big Postgres table to say, can I look up this small string and have I seen that monomer before, has the entire registration normalization. What are the alternate forms of this together? One of the things this then leads to is that people, underestimating the problem, make some interesting and truly hideous bugs. Here, for example, I mean, Biovia, I mean, I shout out or insult the marvelous Celerus people. It turns out, we had an interesting example, what we're showing today, is when you have a nucleic acid sequence, there were phosphoruses placed between, each nucleic acid. In the depiction that was up, there were less phosphoruses than there were residues. So it's interesting, it's like, do the phosphoruses only appear interstitially? It turns out that, for example, where Biovia and PDB split up nucleic acids, includes the 5' phosphorus, where Helm and their default monomer databases define things, put in the 3' phosphorus. Greg will remember this because it was presented at an RD-Kit meeting many, many years ago. The Helm readers and writers that are in version 1 of the RD-Kit toolkit, avoid this problem. They have different flavors for how things get represented. Here, for example, is using Biovia Direct, a nice and expensive cartridge from Biovia that says, well, read in this RNA sequence and show me what the mol file is and depict underneath. The very observant will realize in the center, there's a sugar linked to a sugar with an oxygen bond in the depths of it. I apologize those people on Zoom and Discord, but effectively the representation of how put things together, no one seems to check and double check are the structures they're getting out or how things are being put together work in the right way. So this was then, the RD-Kit solution. My word of advice when people look at or adding Helm functionality to RD-Kit is to wonder, or at least take a look at the implementations that are in there and some of the design decisions that are made. An interesting, for example, is that I apologize. Greg almost, as I said, don't shout out to anyone, but I'll do it once or twice. But in Rachel Walker's talks this morning, she had an interesting variant that was used in one of the slides, which is essentially a sidechain, the DCK. If you try pasting that into Pasteur Alliance's tools, it throws its hand in the air and says, well, DK is not a recognized monomer. The monomer names can handle parentheses. These sequences don't work the same way as smile strings. And that essentially we now have a variant of Helm based from the Schrodinger folks. And then likewise, more generally in the representation issue of how does one handle things like double bonds between monomers, triple bonds, stereochemistry at the interfaces between monomers. For amino acids, things are very simple. The D versus the L amino acids of the alpha carbon are stored in the middle of the monomer. For large numbers of structures, it is the points on the outside of where things are joined together. So as we were saying, the zinc coordination in metalloproteins has an interesting stereochemistry or tetrahedral stereochemistry, but where it is you represent that. Here, for example, glyco-CD forward. One of the solutions I suggest this, or one of the other projects to be added to the issue tracker, if not a hackathon project, is if you haven't seen it before and it hasn't been mentioned an awful lot, is a variant of Helm called inline Helm that is supported by many of the major vendors that basically says, well, if ever you want to inline or hard code a monomer, I can give it in the middle of a sequence. That pretty much says is that putting a smile string or a chemax on extended smiles in the middle of your definition of a peptide or monomer is one of the ways you pass it on in between programs. This ends up being phenomenally useful. It means that files can be transferred without pharma companies agreeing on monomer dictionaries, having translators, boundary issues. All of the Helm, for example, that is found on PubChem and downloadable from there, it uses inline Helm to handle the controversial or the less standard amino acids. I'll skip over this other than to say that even where monomers begin and how they're put together, the Pistono Monomer Alliance, for example, has a group for FMOC and another one for amino acid like alanine. Kemble, when they split up their monomers, ended up with 20 extra ones because they had FMOC-A put together. And so the translation or trying to move them backwards and forwards. Likewise, let's get on the music. Well, hopefully the Zoom folks will shout and complain. But likewise, things like the chemaxon variants of Helm, the heptarase variants of Helm, we're immediately beginning to come across the same standardization problems that Smiles, Molfiles, and others have had. And as I presented previously, is that finding nice ways to present depictions and put them on the screen will be useful. This is another one to mention subtly, or for those people that think that this type of processing isn't possible. Greg will remember this as a tarball or a set of code I sent to him in 2013, where at the time he said, well, no one is really interested in bioinformatics and biology. The world doesn't need sequence alignment. But it's essentially showing the controllable pull request that I'm sure Greg is happy to give out to a student here to try and see what they do. For example, it extracts the sequence from a PDB file. here myoglobin and human hemoglobin, I mean, related proteins, does a sequence alignment using PAM and Blossom alignment matrices, and then an RMS superposition constrained upon the equivalent amino acid positions to spot them on the screen. So for those people working with kinases or kinase series or things from related sets of compounds, this type of functionality that says, well, I can do bioinformatics type analyses. Likewise, one of the things that works underneath the surface in how RDKit or the RDKit implementation of Helm works is the clever use of a PDB residue structure. The predefined or the well-known and undisputed amino acids are reported by their PDB or their 3-letter code. Another hackathon project is that it would be quite easy or trivial to add all of the N-methyl variants and the D-N-methyl variants to the builders through and done. Purely because CDD displayed huge Y problems and the scaling issues on the screen yesterday. Here, for example, is the smile string of an antibody light chain. One of the things it's trivial to do is reduce that to the sequence. They're trying to work out, well, do we draw huge Ys on the screen? But of course, far more useful for people working in antibodies and immunogenetics is actually the complementary determining loops. Which are the important bits of the antibody that determine how it is you link to. I mean, this is the depiction you care about on the screen. These are the free variables for learning. All of the rest is, boilerplate that's put in there. And of course, it turns out that, IMGT and others have interesting depictions or ways of showing this to biologists, where here, for example, loop 1 is shown in red, loop 2 in yellow, another one in purple, and then loop lengths are one of the things that's used on the surface. One might ask, how is it you can go through and extract or identify the complementary determining loops of an antibody? And you realize, well, exactly the same code that Greg had for superimposing kinases and protein structures can be used for working out how to draw interesting antibody things. As we come to the end, last two or three slides, I was going to say something about chemical text mining. The patentizer paper looked interesting, but I realized at the last moment it had no name to structure code in it. It was entire, optical character recognition and optical structure recognition problem. But it turns out, and I apologize to the Bilm and the Helm folks, it turns out that chemists for years have been using perfectly reasonable ways in publications of explaining or describing peptides and peptide sequences. The string pro-gly-phi seer pro-phi arg has been in this PubMed abstract 5,120 from 1976. It's managed to survive 50 years without ever being converted to a chemical structure and doesn't appear in PubChem. And it turns out that very few of the tools out there, neither ChemDraw nor Marvin, nor OpenEye or Opsin, support just the translation of 3-letter codes and hyphens into smiles and structure. And so one of the things going forward, for example, is, well, before inventing a machine-readable file format, try and handle the names that are out there as a way going forward. This one, I should apologize to Jan again. I read one of Greg's blog posts where it started showing some very, very bad structures of an evaluation of bond order perception based on QM9. I'd mistakenly at the time assumed this was Jan's fault. It turns out, no, the smile strings in the QM9 database are truly terrible. But basically saying is that, better evaluations, that doing bond order perception tests on well-minimized quantum structures with hydrogens is the easy case, like shifting fish in a barrel. Working with the molecular dynamics ligands where you don't have the hydrogens or the X-ray crystallography and distorted structures is an interesting or a better benchmark. And here, for example, my apology in big words and letters on the screen to Jan. Of course, the problem is it wasn't actually my algorithm that was implemented in OpenBabel. My one doesn't make those types of mistakes, but I was interested in the time of seeing whether one of the things Jan talked about last year was how well the bond order perception in RDKit matched what appeared in CSD. It turns out that Jan was using the equation 1.3 times covalent radio I plus the covalent radio B. CSD described in their documentation the method that they use is just to add the two together in 0.45. One would imagine almost perfect, matching between the implementations backwards and forwards. Another one for Greg, because he'll enjoy this. I sit in front of him at the ICS and point out the perils of bounds matrices. A marvelous talk yesterday from the ETH Zurich folks. RDKit's bound matrices are very, very poorly constrained. If you take, for example, acetonitrile, you can do a mole from smiles and then print out, a bounding matrix. you see the sets of constraints that are applied by default. And I apologize if it's EKTG versus even EDG. But you notice, for example, a 10–15% difference in bond lengths, especially when we had a talk today on how important getting the fourth and fifth muscle place are. But if you just look at those sets of constraints, acetonitrile, which has no degrees of freedom and should be perfectly linear, is actually the bounds matrix is generated by RD kit allows 155-degree mean angle bond in there. And then likewise, one of the mistakes that's often made, Greg has nodded before and said, no, we don't make that mistake, but the code doesn't agree with him. That the ideal bond lengths, and angles used in molecular mechanics force fields are misleading. They're not the ones that are done. In the MMFF and UFF force field, the bond between two aromatic carbons is the center of a potential well. But the 1,4 distances, the angles, and the bumping into things means that when you minimize, the actual bond lengths you expect in benzene are bigger than the minima that are used in the parameterization. And then finally, just the last one to shout it out. A quick word on Patrick's complaints about the 4-digit accuracy in version 2000 miles. It's a mistake I made. Rasmol, when it did its molecular graphics, rounded all coordinates to integers and rounded them to 256 of an angstrom. The computer scientists will realize what trick was going on there. But it turns out that the remarkable reproducibility of NMR experiments is the result of statistical mechanics. When you look at an NMR experiment, it's many billions of molecules over very long time periods that are being averaged. And thanks to the central limit theorem, yes, you can measure, in reports, the 19F peak to like 14 or 15 decimal places. But the trouble is, any one snapshot you take of a molecule, certainly in solvent at 295, being bombarded by thousands of molecules per second, you're a free rotor. Taking 2 data points and saying, oh, they're not quite the same is not the same as seeing the average. And with that, I shall say that I'm completely done. Greg, clearly with the hook, and realizes yeah, I should say it has been a fantastic UGM. It's always a fantastic joy to be here. A huge number of impressive improvements. And then the joke I was saying to Greg, in a way I was disappointed because I was trying to write this thing, and there's less to complain about this year and previous years. And I was thinking, well, why am I disappointed that this is a glass half full thing? It means that the community is getting better, the talks are getting better. Or as then Greg points out, perhaps I'm just getting more forgiving in old age. It really is better.
You said that. Thank you, Roger. If anybody's bright and not exploded, we have time for a couple of questions. I'm going to start actually. So I just make a side comment. You made some very nice suggestions about the Helm parser and the PDB parser and the hackathon. I think I agree that those are really good projects. It would be really nice if we had the author of those parsers here so that they could do that during the hackathon. So for people who don't know, this is Roger's work. So basically he was creating to-do lists for himself during that talk. So he wrote both of those parsers. So thank you, Roger. Is there an actual question out there? I'm not going to let you reply to that, Roger.
It is the syntax that's used for DNA side chains, but not the one used for peptide linkages. Yes. I had another slide I could have used. Anyone that compared the Pfizer written Helm 1 written in Java with the Cyanogen's written Helm 2 that is written in JavaScript would realize there are a large number of Helm things, even posterior alliance, that are read and written by one that aren't understood by the other and vice versa. In fact, in the original Pfizer paper, some of the example strings they have are no longer understood as valid Helm. It's a wild west. Clearly, Greg and his friends try and impose a standardization in the world. RDKit might be one of the ways of providing a validation, or this is reasonable, this isn't. In the same way as sanitization, the number of insane molecules is, or less sanitary molecules is depleted somewhat.
I feel like so much of my life is walking around behind Roger carrying this so that he can talk. We have time for one more if there's anything. Rachel? You're going to go ahead and ask the question.
Oh. Permission to redirect, Your Honor. She opened the door. Through to the points. I've received enough law and order. Okay, thank you. So to me, the big worry or the concern with the Schrödinger approach of monomer mole is it treats it as, a conversion problem. You have an all atom representation that goes to a monomer problem and a monomer problem goes to all atom. Really, they're different views of the same thing. They should coexist and work at the same time. I was very impressed with data grok, for example, where it moused over the all atom representation and the monomer we showed up and was highlighted. You realize, with the simple or the proposed pull request from Schrödinger, that type of linkage isn't there anymore. Or if you have monomers that you can't quite represent, it's interesting you defined a new, a monomer mole hash because the existing mole hash wouldn't work or wouldn't be sufficient. The duplicate testing, the canonicalization, substructure matching, you realize that so many problems are solved by the chemistry that just having a biological view layer so that people can get, the names to put in patents or an interesting or nice depiction on the screen. But I do think it's a huge step forward. It does look very pretty. I hugely love the sketcher. I should have shouted out to that, but it's again, all great stuff.
Thank you, Roger.